In this video, you will learn how to write down measurements on any state, both pure and mixed. We will treat measurements with density matrices. We can write down a density matrix as a statistical combination of pure states psi-k, where pk is the probability that the state is in psi-k. For a measurement in the z-basis, which is also called the computational basis, the measurement operators are m0 is 0, 0, corresponding to measuring the 0 state, and m1 is 1, 1, corresponding to measuring the 1 state. Suppose we measure the state ρ and we want to know the probability of a certain measurement outcome, let's say a 0. That probability can be calculated by taking the trace of the density matrix times the measurement operator. So if we want to know p0, we should take the trace over ρ times m0. Let's make a little side note here. The trace of a matrix is the sum of all diagonal elements. So if we have the matrix 0, 0, 0, 0, 2, 0, 1, 1, 1, the trace is 2 plus 1 equals 3. Now let's take a look at an example. We have a state psi that is in the 0 state 50% of the times, and in the plus state the rest of the times. We can write down the density matrix as follows. Rho equals 0.500 plus 0.5 plus plus. We can work out this density matrix, which leads to rho is 0.75, 0.25, 0.25, 0.25. So now we want to investigate what p0 is. In other words, if we measure rho in the z-basis, what the probability is to measure is 0. We use the trace formula. So p0 is the trace of rho times m0. We can fill in the density matrix here for rho, and the measurement operator is 1, 0, 0, 0. If we work out the matrix product, we are left with trace 0.75, 0, 0.25, 0, which equals 0.75. Now let's look at a slightly more complicated example, where we measure in the y-basis. We want to answer the question, what is the probability to measure the I state? The measurement operator corresponding to the state I is bra I ket I. So the multiplication of the column vector 1i with the row vector 1 minus I, where the minus sign comes from complex conjugation. Performing the multiplication then leads to this matrix. To get the probability pi, we follow the same method of multiplying rho with the measurement operator mi. Now we can fill in these matrices. 0.75, 0.25, 0.25, 0.25 times 1 minus I plus I, 1. And multiplying will then lead to 0.75 plus 0.25i, 0.25 plus 0.25i, minus 0.75i plus 0.25, and minus 0.25i plus 0.25. Summing up all the diagonal elements will cross out the imaginary terms, which leaves us with 0.5. Now let's talk about the resulting state after the measurement. Formally, we write this down as rho I is mi rho mi divided by the probability pi. So if we measure the state rho in the y-basis, it turns out that the resulting state is I, and this was to be expected for a projective measurement. Let's look at one last example. Suppose our quantum state is the Bell state, the maximally entangled state consisting of two entangled qubits,